Hello guys, this is the first video of my YouTube channel, and we'll start off with a brief introduction into Form 4 AddMaths, Chapter 1, 1.1 Functions. So this is just going to be a brief introduction of this subtopic. Okay, so let's get straight into it. So what are functions? Functions are, let's try to think of them as a machine. They're a machine where if you were to throw something into it, it would throw you back with a corresponding value or corresponding something. It gives you back something. Or think of it as an oven. When you put the cookie dough inside the oven, it gives you back cookies. Or if you were to put a chicken, you would get a roasted chicken. So that's what you could think functions are. Maybe to visualize this even better, we can have a look at these two examples of sets that I've drawn over here. Let's look at the first example. So in the first example, we are given two sets which are x, which are x and y. So these two are two separate sets. However, if you could see in the middle, there are arrows connecting each value to a corresponding value. So our question now is, what helps this number over here, like say the 1, to be linked to this number or to be made into this number? So if I were to throw a 1 into the machine and it gives me a 2, so this is where functions come in. So the functions are the things that transform that input they get and give us with an output we want. So for example, over here, if I were to throw in a number 1, I'd get back a number 2. And if I throw in a 3, I'd get a 4. And if I throw a 5, I'll get a 6. And if you could already try to guess, there is a little relation between these two numbers. And that is, for each object over here, we are getting a value that is one integer greater. So because you could see, for 1 we get 2, and the difference is 1. And when we put 3, we get 4, which is also plus 1. When we put 5, we get 6, so it's a plus 1. So in general, our function is fx, where is equal to x plus 1. X will technically be our object from our first set, and our y, which is our second set, is basically fx. So for every x value that is in the set, it's added to by 1, which gives us the fx value or the y set. Okay, so let's take a look at the second example over here. So in this set, in this example, we're given two sets also, where in the first set we have x, where we have -2, 2, and 3, and in the second set, of which is y, we have 1, 4, and 9. And we could see the -2 and 2 are connected to the 4 over here. And if you could see, the 3 is connected to the 9. So this bridge over here is basically our function. The function takes in our input and gives us an output. And maybe let's try to guess what this function could be. Well, I think if you've already seen it, it's actually fx is equal to x squared, because when you square the -2, you get 4, and when you square 2, you get 4 also, and when you square 3, you get 9. So the bridge, or our function, will be x squared. For every input that is taken, it is squared, which gives us our y value. Alright, so that's just a brief explanation about a visualization about functions. Alright, and one little important thing over here is the function notation. So a function notation tends to not look like the usual representation where we have something like this. This is an equation, a function equation. However, a function notation is different. A function notation is denoted in this way. It's just a different way of writing the function. So please bear that in mind, because there could be questions asking you to write the function notation, but not the function equation. Alright, so this, do bear in mind. So I mean, this will be the function notation for this corresponding function, and this will be the function notation for this corresponding equation. Okay, so let's move into the second important thing that we have to know, that functions can only have a one-to-one or a many-to-one relation. Okay, so to understand what's going on over here, if you could see the examples I gave earlier on, like for example, this 1 gives us a 2, this 3 gives us a 4, and this 5 gives us a 6. And if you could notice, each line that is connecting between the sets is only connected to one corresponding value. They are not connected to two. So basically what we could say over here is one value is connected to one other value, which is the one-to-one function. Okay, if you could like try to get the concept over here, and that's the one-to-one. And we have a many-to-one function, a many-to-one relation, where you can see here we are given a -2 and it gives us a 4, and we also have a 2 that gives us a 4, and we have a 3 that gives us 9. So if you notice here, there are many x values that gives one y value. So these two, one-to-one and many-to-one, are the only possible function relations. You cannot have any other relations that can be called a function. A little tip over here is the type of function must end with a 1. It's just a little trick to know if the type of relation is actually a function. So like you can see here, it ends with a 1 and a 1. A function must only end with 1. Because every function gives us only one value. So we cannot have more than one value. We cannot have more than one values for in the output, In the second set, we cannot have two values for one object. So everything we put inside a function should only give us one object back. Okay, so there are two other relations that I'll show you that are not functions. So let me just try to maybe visualize what is not a function. So I mean, just take a moment to ignore these numbers and just like focus on the dots here. Okay, so if I were to have a one-to-many, where for example, like one value connects to many other values, this is not a function. As well as many-to-many, which means one value leads to this one, two values lead to one, and there are just so many values, and this 2 also leads to another value. So you can't have many values leading to many other values. So this leads to the tip that I gave earlier, to a function must end with a 1 at the back. So a one-to-one relation or a many-to-one relation. These are the only functions. Okay, so let's go into the second part, which is about domain, codomain, and range. Okay, so what are domains, codomains, and a range? So technically, a domain is what is inside of the first set, or maybe you could say the X set maybe. And sorry, wait. In the X set, and the codomain is whatever is in the second set or the Y set. Okay, so there are going to be questions in the exams where they'll give you like this kind of notation or this visualization over here, and they'll tell you to list down the domain, codomain, and range. Okay, so just to rephrase again, the domain is whatever's in the first set, the codomain is whatever's in the second set, but the range is whatever's in the second set, but it must be connected to the first set. Okay, let's just try to solve this one, for example. So the domain in this one will be 1, 3, and 5. The codomain will be 2, 4, and 6. And the range, I mean, if we have to take a look, all the values in the codomain are connected to the domains. So that's why our range will be the same, which is 2, 4, and 6. Alright, so that's our first example. Let's have a look at our second example. Okay, so why don't you take a moment to pause the video and maybe like try to solve this. Okay, so if you've already solved it, the domain for this will be -2, 2, and 3. The codomain is whatever is in the next set, which is 1, 4, and 9. But if you notice, okay, when we come to range, remember what we said about range. Range is whatever's in the second set, but is connected to the domain. So if you have a look again, the only elements in the second set that is connected is 4 and 9. So our range will only be 4 and 9 and not 1. There is no 1 in here because the 1 over here is not connected. It is a part of the codomain, but it is not a range. And an important tip that you should remember is whenever you're given a question to write down the domain, codomain, or range, you should never forget to include the brackets or these curly braces. They are really, really important, and you cannot forget them. If you were to forget them, you'd lose marks and you just get the question wrong. Okay, so maybe let's try to visualize what a one-to-one function really looks like. These are two examples of a one-to-one function. So it's just like a straight line. So I give two examples here, one with a positive gradient and one with a negative gradient. So these are one-to-one functions, and I'll explain very shortly why are they actually called one-to-one. And if over here we have a many-to-one function, and many-to-one functions, this is one of an example where you get a parabolic curve. I think you learned this in the second chapter, which is the quadratic functions. Alright, so these are called many-to-one functions. So, okay, why are they actually called one-to-one and many-to-one functions? Okay, let's have a look. So over here we have a thing called a vertical line test. And remember what I mentioned earlier, that a one-to-one function and a many-to-one function can only be functions, because for every function we can only get one value out of the function. For every value we give into the function, we can only get one corresponding value. So a vertical line test is something that helps us check if a graph is actually a function. So let's say we use this graph over here. Let's try to determine if this is actually a function. So if I were to draw a vertical line like this, and notice how it only intersects at one point. If I draw again, It just intersects at one point of the graph. This proves that for every x value that is given, there's only one y value, because technically whatever that comes out of the function is a y value. All right, and maybe the second example, if I were to draw a vertical line again, I see no other intersections. So this is a function because I only get one y value for every x value in the graph. Okay, and let's try for this one. It's a parabolic curve, and if I were to draw a line, vertical line along the graph, I see no intersections. I see no more than one intersection. I just see only one intersection, and just means one y value for each intersection. Okay, so maybe to explain this even better, I'm going to give you examples of what are not functions, what cannot be functions. So if you have a look at this graph over here, okay, so let's try to determine if this is a function or not. Maybe you could try it on your first, by yourself first. Okay, so if I were to draw a vertical line at any point, notice how it gives us two y values. It gives us two y values, two intersections. And from what we know, a function can only give one output value. We cannot have two output values. So this is not a function. And if you were to draw this somewhere else also, you're getting two intersections. You'll get two intersections. And another example here is this elliptical graph over here. And if I were to draw a vertical line along this graph, you can notice easily that there are always two intersections, which is technically more than one. So this is also not a function because it gives you two y values for every x value, and a function should only give you one y value. So that's about the vertical line test. Okay, so let's jump into the modulus. Okay, and we'll start off with a graphical visualization of the modulus. So let's just have a look at this graph for an example. This is a y equal to x graph, where, for example, if the x is 1, the y will be 1. So this is the graph of y is equal to 1. Y is equal to x. So, and maybe you could try to see it's actually a function because there's no intersections and only intersects once. Okay, and let's have a look. So the modulus, which is technically this box over here, the modulus is technically a box. So if you see this graph y equal to x, a modulus basically converts any negative value into a positive value. So for example, if I were to have -3 inside a modulus, it gives me back 3. If I had a -6, it would give me 6. So if I were to apply this to a graph, okay, I would get this. Okay, now let me explain why do I get this over here. So if you can see here, any positive value in a modulus will give back positive, but negative will give you a positive. For example, -3 will become 3. And for this example over here, if I were to modulate this graph over here, I just put a modulus over here, every corresponding negative x value would convert to a positive value. So that's what you can see happen over here. So this was the initial position of that graph earlier, and once I applied a modulus to it, every negative value in here is converted to a positive y value. So the negative 1 became a 1. Then the negative 1x produced a 1y value. For negative 2, sorry, this is slightly wrong. It should be 2, sorry, 2x. 2x. I just realized that. Okay, so so the negative 5, if I were to wanted to find the y value for this, I just have to substitute it, negative 5, where I'd get negative 10, and gives me 10, because any value inside a modulus becomes positive. So that gives me 10. So with that, I can plot a graph, and I'd get this V shape. Alright? So that's just a brief explanation about the modulus. Any negative value inside a modulus is converted to a positive. Now let's have a look at the second example. And over here, I did give quite a complex graph over here, which is a sine graph, which you don't really have to understand how it works or whatsoever. But this is some sort of shape you will get. A sine graph, a sine x graph. And if I were to tell you to modulate this graph, can you take a moment to realize, or maybe draw it out, how would it look like? Well, if you were correct, it would be like this. So technically, the negative part, or the negative part of this graph, is flipped to a positive part. So it gives you a positive value. Like if you can see the dotted lines over here were the negative value, the initial position. But when I modulated this graph, it became positive. Maybe a little tip to understand how modulation works is just that the graphs reflect about the x-axis, and only the negative part reflects about the x-axis. The positive part is just left to be there, because a positive value in a modulus is remain a positive, but the negative value is reflected to a positive value. Alright? And just as a final part of our brief recap, so we'll jump into objects and images. Now, if you realized, I sometimes use the term objects when in functions, and for every object, an object is something you throw into the function, like the machine, right? You throw something into a function, and the image is technically what you get from it. The y value, your result, that's an image. So over here, I stated object is what you put inside a function, and the image is what you get from the function by the corresponding object. It's more of, you could say, the range. The image is something like a range. Okay, so it's something that you get from the objects that you put inside. So let's have a look at this question over here. So we are given the function notation of fx equal to 3x plus 5 over x, and where condition where x cannot equal to 0. And let's say we were asked a question, what is 5 inside the function fx? So all we have to do is simply sub in our object, which is 5, into the equation, and we'll be given an image, which is 16. The 16 here is our image, is what we get from the function. The 5 is the object. Our 16 is the image. Alright? And you could also get a question, the image of 1/3 under f. So they want you to find the image of the x value of 1/3 using the function f. So technically, all you have to do is sub the 1/3 inside the function. 1/3, which gives us 1 plus 15, and we get 16. Now, one interesting thing about this is you realize that there are two x values or objects that give us the same y value or image. Doesn't that ring a bell to you? This shows that this is a many-to-one function. There are many x values that lead to one y value, and this is a function. Alright? Because it gives one y value for many x values. So this is a type of function, a valid function. Alright, so besides, there are many types of questions you could get in your exam, and not many questions are going to be very straightforward like this, like giving you the object and finding the image. There are instances where they could give you the image and they'll tell you to find the possible objects or the x values. And for example, this question gave us the image, which is 8, and we are supposed to find the image, the object of it, or the x value. So we can simply equate f of x is equal to 8. So whatever we put x value in here into the equation should give us 8. And we can rewrite this equation again, where we get 3x plus 5 over x is equal to 8. Now, as you can see here, this is some sort of a algebraic problem which we can actually solve. So all we have to do is multiply each side by x to remove the x from down here to get 3x squared plus 5 equal to 8x. And we can form a quadratic equation from here, and we can factorize it to give us two x values. So these two x values give us 8. So this is also proof of many to one, because there are two x values that give us 8. So I hope this video helped. It is a really brief explanation about the first subtopic in the first chapter. So I hope you guys found this video valuable, and yeah, please stay notified for upcoming videos. That's all for now. See you.